We introduce a direct volume rendering approach that can render encrypted images directly from encrypted datasets. The rendering is performed by operations in the encrypted number space which are dual to operations in the plaintext space. Therefore, the rendering system does not need to decrypt the data. This homomorphic volume rendering approach makes it possible to use untrusted servers for rendering without compromising privacy.
We present columnar data augmentation through visual analytics. Kava lets users augment their data with additional attributes found on knowledge graphs. To construct a new attribute, each row of a dataset is mapped to a node on a knowledge graph. Each augmented datum is the result of a query over the knowledge graph in the neighborhood of that node.
Given a dimensionality reduction scatterplot, we project its original subspace. Through the orientation and shape of our glyphs, both the global trends and local patterns can be identified. To transform the vectors, we use implicit function theorem. We apply our method to different kinds of data.
We present our work on data visualization, a technique which helps facilitate understanding of physical measurements and quantities by providing visceral experiences to users in virtual reality. This allows them to experience the ground truth of what the data is in reality, as compared to the abstract nature of conventional data visualization. We hope our work will spur new considerations into how immersive technologies can be used for visualizing information, and that you will find it interesting.
Being able to perform visual analysis on sensitive data in a privacy-preserving way has become more and more important. In this work, we look at two major research questions in differentially private data visualization towards better understanding of the relationship between the privacy parameter, visualization type, the analytic tasks, and users' performance through cross-source user study and simulated comparisons.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. Connect to the data you care about. Sort, highlight, drill down, or filter your data in seconds. Add calculations to extend your data. With Tableau, you can keep on asking questions in the data until you discover the root cause. Tableau. Answer questions at the speed of thought.
The mixture graph is a data structure for compressing, rendering, and querying segmented volumes. Biomedical segmentations have evolved from mere annotations to first-class modalities. The mixture graph stores the computations required to render such nominal data directly on the GPU, including pre-filtering and lighting. Segment distributions can be queried efficiently using regions of interest.
Right. Hello, everyone. Good afternoon in the Utah time. So welcome to the Deep Learning for Spatial Data session. I'm Hanqi from Argonne National Laboratory, and I'm very honored to chair this great session. So in this session, we have 6 amazing papers to present. These papers are from both VIS and TVCG. So each paper will be presented for 12 minutes, and then we will have a 3-minute short Q&A after each presentation. So if you have any questions, you don't have to wait until the end of the presentation to leave the questions in Discord or YouTube chat. So the YouTube chat and the Discord will be synchronized bidirectionally with each other. Let's move on to the presentation. So the first presentation is the deep volumetric ambient occlusion. So it will be given by Dominik Engel.
Hello everyone, my name is Dominik Engel. I am from Ulm University and I have the pleasure of presenting you our recent work, Deep Volumetric Ambient Occlusion. So as the name suggests, we're trying to solve the problem of ambient occlusion, and more specifically volumetric ambient occlusion. That means we take any input volume I, and for each voxel in this input volume we want to predict the correct ambient occlusion value. Now the idea of our paper is to frame this problem as a supervised learning problem. That means we will train a deep neural network in order to solve the task for us. So let's see how the data looks like that we use to train the network. So first of all, of course, we need volume data. For this, we use the CQ500 dataset by CureAI. This is a large collection of CT volumes of human heads, and we have paired those with randomly generated transfer functions, as you can see in the middle. Lastly, given pairs of input volume and transfer function, we have computed an expensive ambient occlusion ground truth just by raycasting along 1,000 directions for each voxel and computing the ambient occlusion value individually. Having seen the data, let's look at our network. So as we're dealing with a volume-to-volume learning task, we are basing our architecture on the 3D UNet. That means this takes a 128 cubed intensity volume as input, encodes it using the convolutional encoder to a latent representation, and then it gets decoded back up to a 128 cubed ambient occlusion volume using the decoder. Now, each of those blocks consists of 2 mesh activation, instance normalization, and 3D convolution layers. And as is usual with units, in between all those blocks of different sizes, we do up or down sampling, and we also have the skip connections from the encoder to the decoder wherever the resolution matches. Now, this architecture isn't quite able to solve our problem right away, because we only have an input for the volume. However, in order to get a correct ambient occlusion volume, we also need to know the transfer function. So we need some way to bring a transfer function into the network, or as we'll see in our later evaluation, what we are introducing basically would work for any kind of additional global information. We're demonstrating it at the example of a transfer function. But first of all, how do we usually represent a transfer function? So there are 2 very common ways. The one is the 1D texture. We're just mapping intensity to opacity. Note here we are disregarding RGB entirely, since we only need the opacity for the ambient occlusion computation. On the other hand, we have the point-based representation, which is what you usually know from a transfer function editor widget, where you place the points and interpolate in between. Now, the 1D texture, while being a very easy to handle structured format, it is also an inefficient representation. That means most of it is sparse and well 0. And we also need to ask the question of at what resolution do we want to use a transfer function. Not so nice things. For the point-based representation, what we can say is it is very compact. It is not as inefficient as the 1D texture. However, it is unstructured. That means we can have a varying number of points in a transfer function. That makes it a little bit harder to deal with in terms of neural networks. But we'll see how to get around with this. Then, however, as we've seen before, we are using a 3D CNN, and none of those representations are quite obviously compatible with the CNN. So what we've done is we have created intermediate representations for the transfer function, and we have looked at ways at how to get those into the network. So let's look at those. For the intermediate representations, we have split those into implicit and explicit representations. The implicit representation being when you take this additional global information, in our case a transfer function, and you represent it implicitly in a volumetric shape. That means we get a volumetric shape input, and also we are relating the transfer function information directly in a spatial sense by assigning individual voxels individual values. So luckily for the transfer function, the implicit representation boils down to applying the opacity transfer function to the intensity volume. And for the explicit representations, we are using the previously mentioned strategies, and we're building extra neural networks on top of those in order to extract a fixed size vector, fixed size learned feature vector from it, that we're training so that our network understands it. And the good thing about this is a very compact representation of the transfer function. We can make it as compact as we like, and this may also be used for other tasks together with other networks. In the case of the 1D texture, we've just used a 1D convolutional neural network to extract this fixed size vector. In the case of the point-based representation, we have used something PointNet-like, a technique that comes from point cloud learning. It will deal with the unstructured nature of the data. Then, having those two representations, let's look at how we get those in the network. We call this injection strategies. And our first injection strategy with the implicit representation is the pre-classified strategy. What we do here is, instead of feeding the standard intensity volume into the network, we apply the opacity transfer function, we get the opacity volume, and we feed this into the network. For the global concatenation, we take this very opacity volume, We rescale it to all spatial resolutions that are present in our network, and then we inject those through the skip connections into the decoder. As for the explicit representations, we have dilated concatenation. Here the idea is we take this global feature vector, the TF descriptor, and we want to combine it with the volume, or also with a global feature descriptor of the volume, which we luckily get right in the middle of our unit in the latent space. So we're concatenating the global TF information with the global volume information in the middle of our network, and then we hope that the decoder can reconstruct an ambient occlusion volume using this combined information. Lastly, we have looked at adaptive instance normalization. So what this does, first of all, as we've seen in the base network, we have a lot of instance normalization layers in our network. What they usually do is we learn a scale and shift to normalize the feature maps during training. And adaptive instance normalization on top, it doesn't just learn the scale and shift directly, but it predicts it from the transfer function descriptor. So basically, we're modulating all our decoded feature maps using the transfer function information. So now that we've seen basically all that we need to train a network, so we have data, we have an architecture, we're about to look at a loss function. Let's see at how we trained this. So as I said, first of all, the loss function, we have also evaluated this quite extensively. In the end, we found that a combination of structured dissimilarity index and mean squared error works just fine. Then next, we used mixed precision training for our network. That means instead of the usual 32-bit floating point precision computations, we do most computations in 16-bit float, which makes it a lot faster and also saves basically half the memory. Then we were able to train the network on one RTX 2080 Ti in around 20 hours. And for this, we have used the rectified Adam optimizer with look ahead, a combination also known as Ranger. So now that we know everything about how we can train this, let's look at our results. So here we can see a rendering and an ambient occlusion volume of our ground truth. And we can compare those with our proposed approaches. Note for the explicit representations, of course, we have used all combinations with both the 1D texture and the point-based representation, which is showing examples here to make the slide a little less cluttered. So as we can see, the pre-classified strategy is what works best. It gets closest to our ground truth, while in general the explicit strategies are a bit on the blurry side. However, they run faster, so you can make a trade-off here. Then let's also look at some interactive examples. So here we can see our technique interactively rendered. On the left you can see the final rendering, and on the top you can see the ambient occlusion volume only. If we now change the transfer function on the down right, you can see how the volume adapts. And if we use this little run button right here, we trigger our technique. As you can see, we get a very reasonable ambient occlusion for our CT volume. Now, we have trained the technique on CT data mostly, but we can also generalize to other modalities like magnet resonance imaging and electron microscopy, as you can see here. And lastly, what can you take away from our work? Well, first of all, if you're trying to combine any kind of additional information with volumes, you should first try to represent implicitly in the volume if you can. Otherwise, or also, you should not just forget about these explicit representations just yet, because they are, while performing a bit worse in our experiments, they are faster, more compact, and also just bring new opportunities, given that you could use those learned descriptors for other networks as well. Then we have seen we can generalize to other modalities despite only training on CT data. And we would encourage you to look at this structured dissimilarity index loss for any kind of regression on visual data, really. And lastly, you should also check out Mixed Precision just to get this 3D CNN training feasible in the first place. Yeah, thank you for attending my talk. You can find all relevant resources on our project page, which is dominikengel.com/dvao.
Okay, thanks for the very nice presentation. So we got one question from the audience. So how stable is the prediction of AO if the network is applied to time-dependent data?
First of all, thank you for the introduction. As for the question, it happens that we are producing this ambient occlusion volume. That means we have a view-dependent ambient occlusion here. That means we don't quite have any differences if we change the view. If we have any stability, if we have time-dependent data, we can actually not tell. We haven't tested this on spatially varying data.
Okay, thanks. So we have another question from Anders Enderman. So did you make any error comparison?
Yeah, so we compared, of course, our ambient occlusion volumes with the ground truth. That means the volumes directly. And yeah, with our best method, we can get around a structured similarity index of around 0.9 and a MSE of, I think, 0.07 or so.
Mm-hmm.
Yeah, there's a table in the paper.
Okay, thanks. I have another question. So can you comment on the scalability of the method? So is because you use convolutional neural network, so is the input and output layers are at fixed resolution? So what happens if we have a larger data to work on?
So how we're doing it right now is we render the normal volume in the standard high resolution, and we just do the ambient occlusion at 128 cubed. This is because we are limited by memory in our 3D CNN because it's so computationally expensive and also memory expensive. So yeah, the approach can't cope with state-of-the-art numerical methods at the time, neither in terms of memory nor computation speed.
Mm-hmm.
But yeah, we can scale it maybe a little larger if we get bigger hardware.
Sure, that's for sure. Okay. So looks like we someone is typing another question. So have you? So yeah, the question is coming. So would the same method apply to other approaches such as the photon mapping?
Like a lot more expensive pre-computed volumetric representation, you mean? Yeah, we have tried to do similar things on global illumination. We haven't quite succeeded in this directly. We guess because it's we don't have the amount of network capacity that we might need to do such a thing. But I guess if we can scale it up, it might be applicable to photon mapping as well.
Okay, that sounds good. So I think that's about the time for this paper. Thanks, Dominik, for good presentation and also for the nice answers to the questions. So our next paper is a fluid flow dataset for machine learning and its application to neural flow map interpolation. So Jakob will give the presentation.
Hello everyone, I'm Jakob and I'd like to welcome you to our presentation of our work, a fluid flow dataset for machine learning and its application to neural flow map interpolation. This work was done at ETH Zurich together with Markus and Tobias Günther. In the last decade, machine learning algorithms pushed the state-of-the-art methods in different fields forward, like computer vision, natural language processing, and computer graphics. And visualization was extensively used to explain what, for example, networks were learning by visualizing, for example, filter weights, clusters, and so on. However, the vice versa, namely using machine learning for visualization purposes, has just begun recently and is at the early stages compared to fields like computer vision. This is partially due to the fact that there are no large datasets available for machine learning purposes. Especially for flow visualization, the datasets either need to be first created for a specific problem, relying on a parametric model, which might not generalize well, or the model is simply overfitted due to its small amount of data. Therefore, we made following contributions. We created a 2D dataset to spur more research in machine learning for flow visualization, which covers a wide range of fluid dynamical processes. To demonstrate its usefulness, we apply the data to a Lagrangian transport analysis using supervised machine learning and evaluate the method on numerically simulated and measured fluid flows that have not been seen during training. Before we talk about the application of the data, let us first look at the creation of the dataset. Our dataset consists of 8,000 velocity fields of 2D unsteady fluid flows. They have periodic boundaries and are incompressible. They have a resolution of 512 by 512 by 1001, and they consist of more than 16 terabytes of data. They cover a wide spectrum of Reynolds numbers. Additionally, the dataset can be further processed to derive other fields. For example, for our application, we traced flow maps and trained a network on them. Its usability is beyond machine learning and could also be used for research on feature extraction, for example. So, let's begin with the dataset creation. We wanted the dataset to have following properties. The dataset should include all types of flow features as vortices and separatrices. The sizes of the structure should vary, and the flow should move differently over time. Furthermore, we also wanted it to be periodic with respect to spatial boundaries. This way, tracing of particles is always possible without any concerns about the boundaries. In order to generate different flows, we subdivided the creation process into two parts. The first one is about the initialization of a flow, and the second one is about what kind of solver we use. As we work with divergence-free flows, we can initialize the flows with the cogradients of stream functions. Cook and DeRose proposed a method to create scalar noise fields for different frequency bands. An example for a noise field is shown on the left lower part of this slide with its energy bands on the right side. Divergence-free vector fields are then obtained from the cogradient of the scalar fields. After scaling the frequency bands, we can sum up the bands to obtain a vector field that adheres to Kolmogorov's energy spectrum. Here is an example where we sum up the first 4 energy bands by applying the Kolmogorov energy formula as done by Kim and colleagues. We can thereby limit the number of bands to resolve a flow up to a desired Reynolds number. So, in terms of initialization, we uniformly pick the Reynolds number for each of the 8,000 flows and initialize the frequency bands accordingly. Once we had the initialization, we used the Garry's flow solver to simulate the flow over time. We parallelized the simulations on the Leonhard cluster at ETH Zurich. The simulations of the whole dataset required 1,116 odd hours. Let's now turn to the application. Lagrangian transport analysis is fundamental for flow visualization. For example, the finite time Lyapunov exponent, abbreviated as FTLE, visualizes how particles separate from each other after tracing them for a specific duration. A compact representation of that are flow maps, which store positions of particles on a grid after desired time duration. An example of a particle's position after a certain time is depicted in this small animation. Consider such a transport analysis in a high-performance computing setting. The traditional way would be to copy the entire flow from the supercomputer to a local computer and to trace trajectories there. This yields accurate results, but is slow and demands a lot of memory. In order to speed up things and reduce memory consumptions, time steps can be skipped. However, this yields less accurate results. To get accurate results, speed and low memory, the simulation and the tracing are computed on the supercomputer and the trajectories are then transferred to the local one. This setting is an example for in situ visualization. Once the flow maps are computed, values in between grid cells are inferred by interpolation, which is prone to errors. Assuming we would like to know the location reached from the central seed point, a simple linear interpolation would result in the blue trajectory, while the red one would be the ground truth. A higher resolution of the flow map would reduce this error, but creates higher tracing cost. In order to avoid the cost, we would like to use neural networks in order to upsample a low-resolution flow map to a higher one. This process is known in the computer vision community under super-resolution. Super-resolution for images is a long-standing difficult problem, as any other form of extrapolation. Since neural networks outperform different forms of interpolation methods like the cubic one, numerous works have been studied in the computer vision community. We studied two established state-of-the-art CNNs for images, namely SRCNN and ESPCN. Our flow maps distinguish themselves from images in the value ranges and periodicity. Whereas images have values between 0 and 1, or 0 and 255, the values of flow maps can go to the limits in both directions, though they share properties like grid structure and local neighborhood information. To this end, we wanted to investigate in an ablation study how well flow maps work on these networks and how well they generalize to different domains and flows. It is therefore crucial to have a good normalization strategy. Please check our paper for more information on that. On a high level, the difference between SRCNN and ESPCN is that SRCNN goes through a pre-processing step where it first upsamples a low-resolution bicubically, which is then the input to the network, while ESPCN takes the low-resolution input directly. Second, ESPCN has additionally deconvolution layers with subpixel convolutions. We show here the ESPCN architecture, where the input is a low-resolution flow map and the output is a high-resolution flow map. We optimize over the MSE between output and ground truth flow map. In the next few slides, we would like to show some results. We compared cubic interpolation with SRCNN and ESPCN for upsampling sizes 2x and 4x. We begin by showing the comparison of cubic interpolation and ground truth for one of the flows in our dataset. On the left side, you see the name of the flow. The bluish map is the error map with the metrics MSE and PSNR. Next to it, you can find the FTLE of the flow. Here are the comparisons with SRCNN. And finally, the comparison with ESPCN. Next, we want to see how well the network works on unseen data. That is our flow dataset general enough? The first flow, which is not in our training set, is the Businesque flow, which is also a numerical simulated flow. The second one is the cylinder flow, which is also a numerical simulated flow. The third one is the double cylinder flow, which is also a numerical simulated flow. Until now, the domains of the flows were quite similar to our training set. However, how do the networks perform on simulated and measured data that have multiple orders of magnitude bigger domains? The ocean flow is simulated, however, its domain is quite larger than the training set. Still, the results are consistent. Here we see the airflow around the Guadalupe Island, which was reconstructed from satellite images of cloud movements. Not only is the flow in a vastly different order of magnitude, it is also quite noisy. Due to our scaling to a unit domain, the neural networks produce meaningful results here too, demonstrating their generality. In conclusion, we introduced an unsteady 2D fluid flow dataset for machine learning purposes that consists of 8,000 flows and 16 terabytes. With it, we trained and evaluated two super-resolution CNNs to support Lagrangian transport analysis. We applied the methods on unseen numerical simulations and got better results than cubic interpolation. This work is a testbed for other data-driven approaches, and the dataset could be useful for benchmarks of feature extraction algorithms. Future work are following points. We would like to extend the data to flows with obstacles or boundaries and 3D. We also plan to explore losses or spaces to get rid of grid artifacts. We would like to also look into flow map concatenation and multi-resolution prediction. It would also be interesting to use the data for data-driven feature extraction problems. The dataset can be downloaded under the following link. With that, we would like to thank you and wish you a very nice virtual conference.
All right, thanks, Jakob, for the nice presentation. So we have questions from audience about the data set, and Jakob already answered in the chat that the data set is available online. And we got another question about, is it possible, or what are the challenges to extend this work to 3D flow, even for smaller ones?
Yeah, thank you very much for the introduction, first of all. Yes, the challenges for the 3D data sets is that you have to have enough space, but other than that, it will take a lot of time, of course, more than 2D, but other than that, the challenges are pretty much the same as in the 2D one.
Okay. Okay, so while we are waiting for more questions, I have one. So you train your FTLE or flow map interpolation super resolution network with incompressible flow and flow with periodic boundary conditions. So I wonder, have you tested to generalize this network for flows that do not have periodical boundaries, like ocean flows? When the flow near the shore area, there is boundary. So what are the capability of generalization for this kind of a flow and also for compressible flows?
Thank you very much for the question. So the thing is, with periodic boundaries, we use them to create the flow maps. So if you have flow maps of these flows that you want to upsample, then the thing what the network does is it will look at the receptive field, and the output will be smaller than the input, of course, right? And the thing is, if you don't have a periodic flow map, then you can't pad it in the input. So what we did for our application is we padded it for the input such that we get the same output size as the input size.
Okay.
Yeah.
Right. So, okay, so it looks like we don't have more questions from the audience. So, all right, so thanks for Jakob for the nice presentation and also for the nice answers to the questions. We can move to the next paper. So the next paper is the V2V, deep learning approach to variable selection and translation from multivariate time variant data. So the presentation will be given by Jun Han from University of Notre Dame.
Hello everyone, I'm Jun, a first-year PhD student at the University of Notre Dame. Today I will introduce a deep learning pipeline for variable selection and translation for multivariate time variant data translation and analysis. So first, for image translation, which means we can translate images, we can translate labels to street signs. We can also translate black-white image to colorful image. We can also translate ages to photos. So if we apply this concept into multivariate time variant data, which means that given a multivariate time variant data set, for example, combustion, and a source variable misfraction, we aim to synthesize the rest of variables in the same simulation. For example, the heat release variables, the chi variables. And if we can if we can do like that, we can reduce the number of simulations, and we can also reduce the disk storage for saving these variables. So to achieve this goal, we propose V2V, a deep learning pipeline. It consists of 3 stages. The first one is feature learning, which means we first extract all the variable features through an autoencoder. These extracted features can help us detect the transferable variable group. And once we can find this group, we can construct a translation graph that can help us detect the source variable and the target variables. Once we find these source and target variables, we can apply variable translation so that we can translate the source variable to the target variable. In particular, in feature learning, we first leverage a UNet to extract all available variable features through reconstruction. In the UNet, we first apply 4 convolution layers to downscale the input and compress the input with a 1D factor with 512 components. Then we apply 4 convolution layers and 4 convolution layers to upscale the 1D factor to reconstruct the data. And then we use mean squared error to optimize UNet by computing the difference between the original data and the reconstructed data. Once UNet is converged, we can generate these variable features, and then we apply t-SNE to project these features into a 2D space. In that space, we can measure the similarity of these variables, and this similarity can guide us to select a transferable variable group. As we show in this figure, for the ionization dataset, the detected variable group is H+, He, and He+. So once we detect the group, we can construct a translation graph to help us identify the source variable and the target variable. In particular, we define the transferable difficulty of variable j conditioned on variable I using carrier divergence. Here, we assume that the translation order will impact the following translation quantity, and we will evaluate this hypothesis in the following experiments. As for the construction algorithm, given a pair of variables, we first compute the equivalent distance of these 2 variables in the feature space. The distance determines whether or not the 2 variables are transferable. If the distance is less than a threshold epsilon, then we compute TD for these 2 variables and determines the transferable orders in the following task. So once the transferable order is determined, which means we know which one is the source variable and which one is the target variable, then we can leverage a generator and a discriminator to learn the mapping function from the source variable to the target variable. In particular, in our generator, we apply skip connection to concat the features in the decoding path to the feature in the encoding path to the decoding path. Instead of directly using skip connection, we also apply residual blocks in the skip connection so that the concat features will be more close to the target variables. And in the discriminator, we also use several convolution layers to downscale the input and use a global average pooling to compress the feature into a 1D factor with 1 component, and this 1D factor will demonstrate the realness of the input data. In order to evaluate our approach, we first compare an information-aware approach for variable selection, and we also compare 3 baselines for variable selection translation. These 3 baselines are histogram matching, P2P, and cycle gain. For the comparison of variable selection, the information-aware approach suggests that it is easier to translate chi from YH, while ours suggests that we should choose misfraction to translate chi based on the translation graphs. And here we can find that our translation graph is a direct graph, while the information-aware presents an indirect graph. And the difference is that because we found that the translation orders is very important for the translation quality. So considering the order of different variables is still very important in variable translation task. And here we use the same network to train these two variable pairs and compare the four rendering results. As we can see that our suggested variable pairs can achieve better feature quality compared with the results from the information-aware approach. And in the following video, I will display the feature results of the whole sequence. And for the evaluation of variable translation, we compared three baselines: histogram matching, P2P, and CycleGAN. As we can see, the histogram matching results are totally fail to capture the features compared with the ground truth, while pixel to pixel and CycleGAN are still good enough to capture the details of the compared with the ground truth. And in addition, we also found that the results of CycleGAN is worse than P2P because in CycleGAN, cycle consistency is considered during training, which means give the source variable, we first translate into the target variable, then we also assume that the target variable can also be transferred back to the original variable, to the source variable in CycleGAN. And this cycle consistency will hurt the performance because the translation order will impact the translation quality. And in the following video, I will display a frame-to-frame comparison between V2V and histogram matching, pixel to pixel, and CycleGAN. As we can see, for histogram matching algorithm, it can generate good results in the early time steps, but in the later time step, it becomes worse and worse because when we infer the later time steps, we don't have any ground truth. We can also use the results from the previous inferred results. Then the error will be accumulated in the inference as the time step goes. Here, we also compare the quantitative results in variable selection and translation using PSR and SSIM. Both metrics demonstrate that our approach can achieve higher scores compared with other approaches. For example, for SSIM, we can achieve 0.829 when we translate misfraction to chi, while information-aware approach can only achieve 0.607 when it translates 1H to chi. And finally, we also evaluate how the variable orders impact the translation result. Here, we use the combustion dataset and choose two translations, misfraction to chi and chi to misfraction. As we can see, the translation from chi to misfraction is unsatisfactory since the synchronized isosurface failed to capture the interesting features compared with the ground truth. However, the translation from misfraction to chi is successful since the generated isosurface is very close to the ground truth. We guess that this asymmetric translation is likely because the important information in misfraction is richer than that in chi. Here we also report the TD, the TD values for different translations. And we can also see that the translation from misfraction to Chi achieves a low TD values. And to conclude, we propose a comprehensive pipeline for variable selection and translation for multivariate time frame data. And in addition, we also achieve better virtual quantity compared with histogram matching, pixel to pixel, and cycle gain. This work was supported by US National Science Foundation and the NVIDIA GPU grant program. So thank you for listening. If you have any questions, feel free to ask. Thank you.
Okay, thanks for the interesting talk. We don't have a question from audience yet, but I will start with a couple of questions.
Okay.
So in my understanding, you use the UNet to do the feature extraction part. So
Yes,
why did you choose use another GAN network as opposed to UNet to basically do the variable translation?
Do you mean that why don't we choose another model to do the feature learning part, right? It's not for the variable translation.
Yeah. Mm-hmm.
Okay, so that's a great point. Actually, we tried different architectures for this feature learning part. We tried fully convolution neural network and UNet and GAN, these three kind of models to extract the features from these variables. And we found that actually UNet and GAN achieves similar performance for the reconstruction quantity. However, UNet achieves requires less computation time to extract the features. So here we just use UNet to extract the variable features and use t-SNE to project the features.
Okay, so basically you separate the data reconstruction part with the the graph.
In GAN, it contains two models. So you want to go loop through a generator and discriminator, so it will require more computation time rather than just use a single generator, for example, UNet.
Okay, thanks. Okay, so I have another question. So can you tell more about the directed graph? So is that graph time varying? And I also see some cycles in the graph. So can you elaborate more on how to interpret this kind of graph?
Okay, so actually this graph is from the t-SNE projection. So once we have the t-SNE projection, we can just use compute the distance in the projection space to check whether these two variables could be translated. So if we could translate, so we can compute the K divergence. We just want to see which variable is easy to translate to another, because unlike image to image translations, the source image and the target image has very similar colors or shapes or semantic information, but this is not the case for the variable selection. Two variables could totally have different content or texture. So here, we just want to confirm which pair would be easier for our fee-to-fee approach. So that's why we need a direct graph rather than undirected one.
Okay, that's interesting. So we still don't have a question from audience. So if anyone has a further question, feel free to leave a message in Discord. So we will move on to the next presentation. So next presentation is the VCNet deep volume composition. So the presentation will be given by Yifan Wang from Wang State University.
Hello everyone, my name is Yifan Wang, a PhD student from the Department of Computer Science, Wayne State University, United States. This work is collaborated with the Department of Radiology, Wayne State University. Today, I will present our paper, VCNet, Deep Volume Composition Networks for Segmentation and Visualization of Highly Sparse and Noisy Image Data. This is today's outline. In our paper, we proposed a method to better extract and visualize the complicated 3D macrostructures in the raw and wild images in high accuracy and efficiency, such as acquisition of the in vivo macro-level 3D vasculature from MRI data. The difficulties of the macrovasculature analysis lie in high sparseness of vessels in large 3D volume images, high noisiness such as low SNR, the ultra-tininess of the vessel diameter, as well as the sophisticated vessel system topology. Traditional model-driven methods are easily overwhelmed by tedious manual parameter tuning and post-manual labeling, which are very time-consuming and labor-intensive. While today, we introduce a new data-driven deep neural network, VCNet, that is specifically designed to segment and visualize high-fidelity 3D macrostructures from noisy volumetric medical images in high efficiency. Our VCNet is the new visualization-guided computing paradigm that jointly takes advantages of both direct 3D volume processing and volume rendering clue, MIP. It integrates the strengthened vessel continuity on MIP plane with the direct 3D vessel segmentation in volume to enhance the final vessel connectivity and macrovessel capture. For instance, vesselness algorithm, region growing techniques, nonlinear subtraction, template-based predictor-corrector algorithm are the classical model-driven methods, which require persistent human intervention and thus labor-intensive and lack of cross-dataset robustness. Enlightened by the modern machine learning and deep learning techniques, several research works show deep neural networks' great potential in vessel segmentation, deep vessel, uception, deep VesselNet, as well as VGN, take advantages of the general object segmentation techniques in computer vision field, and some of them rely heavily on empirical experiences, thus do not fully address 3D vessel segmentation challenges. More related works are discussed in our paper. In the following section, I will introduce our VCNet framework and our datasets in detail. Our VCNet applies the dual stream component, which are 3D volume segmentation stream and a 2D MIP segmentation stream, and the bidirectional operation between these two streams, which are 3D to 2D projection and the 2D to 3D on-projection, to track vessels in space and plane domain separately, and integrate them in the final joint learning stage to acquire the vessel segmentation in high accuracy and efficiency. In practice, we divide the large volume images into patches for training due to hardware limitation. The 3D volume segmentation stream is the major stream in VCNet learning to segment the vessel directly in patch volume. We here choose a 3D UNet-like network to embed the 3D vessels into high-dimensional features before joint learning, since 3D UNet is the most stable and robust medical image segmentation state-of-the-art. Our main idea in VCNet is to justify how the enhanced vessel continuity on 2D MIP plane will benefit the major 3D segmentation. 3D to 2D projection process here is to prepare effective and adequate MIP input for MIP segmentation stream. Here we choose the doctor's convention to compute the patch MIPs in axial plane. We compute 5 sliced MIPs, which could lead to significant information loss. We then compute multiple MIPs with slice coverage overlapping. For input patch with 16 slices, we compute 6 5-sliced sliding MIPs. In order to maintain the spatial domain in the 6 MIPs for later back projection, we tail them into a compositive MIP with larger spatial size to match 2D CNN stream learning paradigm. As a counterpart of the main 3D volume segmentation stream, we adopt a half-channel 2D UNet in compositive MIP stream to segment the brain vessels on 2D MIP planes regulated by the dice similarity defined on 2D MIP plane. In order to achieve deeper and more effective integration between 3D and 2D segmentation streams, VCNet intends to merge the high-dimensional features in hidden embedding space rather than the final probability computation. Consequently, we need to unproject the feature vectors on 2D compositive midplane back to 3D patch volume, which is implemented in our customized back projection layers. In these layers, given a 2D compositive MIP vessel features with 32 feature channels in our case, VCNet first disassembles it to features of original 6 MIP slices P1, P2, and so on. For each MIP feature, we use the pixel index information recorded during the 3D to 2D process to unproject the MIP pixels back to their corresponding voxel location in volume as P1, P2 show here. The MIP slice coverage overlap compensates the information loss caused by MIP projection compression. The final patch volume feature fusion is done by choosing the max value in overlapped slices restored from different MIPs along each feature channel. We finally convert the 2D compositive MIP feature to 3D volume domain by concatenating it with the vessel feature from 3D volume segmentation stream along feature channels. A final unified high-dimensional joint embedding is constructed. By applying two convolutional layers on this joint embedding, we can get our final vessel mask prediction with enhanced connectivity. The final prediction is constrained by dice similarity defined in 3D patch volume. The entire VCNet is shown here, and L is the loss function of the entire VCNet, which is a weighted sum of the two aforementioned dice loss functions defined on both 3D volume and 2D MIP plane. The experiments include one public TubeTK MRA dataset and one clinical macro MRI dataset under our collaboration. The latter contains MRVG and SWI images, which enable us to be the first one to segment and differentiate brain arteries and veins and demonstrate our VCNet's potential in extracting macro-level vessels. The vessel labels from macro MRI dataset are refined using our customized labeling tool with real-time MIP contextual guidance and 3D vessel global rendering, and consequently have less omission and more continuity. Here are the qualitative and quantitative result comparison among several methods on TubeTK MRA dataset. Within real-time scale, our VCNet outperforms all other methods on 3 metrics as shown in this table. For example, the key different parts are marked in circles in corresponding qualitative comparison with 3D UNet and Deep VesselNet. With 2D MIP compensation, our prediction is more continuous than standalone 3D UNet. The overall prediction is also much clearer than that of Deep VesselNet. Here are the major level arteries and major level veins in micro MRI dataset. We can see even though the ground truth vessel label is directly refined based on these two model-driven methods, our VCNet prediction is still much clearer with better connectivity. Our VCNet also shows great potentials in macro-level vessel segmentations. Here is the whole brain vessel segmentation results with mid-brain sub-area comparison with ground truth. Please note that the SWI images contains both macro-level and major-level vessels. Here is the comparison with 3D UNet on macro-level vessel segmentation with zoomed-in patches and corresponding error maps. Our method shows better connectivity and less false positive as circled. Here is the comparison with a model-driven ATRG method on macro-level vessel segmentation with zoomed-in patches and corresponding error maps. Our VCNet has much better performance in macrovessel extraction as shown in zoomed-in patches. Here is the animation showing joint 3D visualization of major-level arteries and veins, as well as the macro-level vessels from our developed visualization tool. In this work, we have proposed the VCNet, a deep neural network, to extract and visualize high-fidelity 3D cerebral vascular structure from highly sparse and noisy images. Our VCNet can strengthen the sparse 3D vascular representation by better capturing the small vessels as well as improving the vessel connectivity, which outperform the state-of-the-art classical and deep learning-based methods. In medical practice, this work can be used as the key functions for real-time in vivo segmentation and visualization of 3D macrovascular structure to improve macro-MRAV diagnosis of vascular diseases. In the future, we will extend the MIP-based volume rendering into more general scenarios. Thank you for watching.
All right, thanks for the presentation. So I will start with a question. By the way, I mean, the vessel segmentation results look really convincing for this noisy type of medical data. So my question is, you use like a 3D convolutional neural networks, but for your data, the z-axis or the, I mean, I only see like a 16 axle planes. So how did you do the padding to ensure the quality of the training and inference?
Okay, thank you for your introduction and your question. As we know, the brain MRI data usually have a larger or say higher spatial resolution on the axial plane. So when we do the patch-wise training in our network, we tend to extract a larger spatial size on the axial plane and a small size on the vertical axis to guarantee a larger plane for the or say a larger size on the axial plane to contain more information of the vessels. And the axial plane is the plane where the domain expert examines the vessel, which is better from other projection or the point of view.
Okay, so I will. Okay, I have another question. So, can you talk a little bit about the collaboration with the domain scientists? Basically, what are their roles, and how did you choose? I mean, make the decision to use the MIPS to do the segmentation.
And okay, thank you for your question. And like I said before, the reason why we are choosing the maximum intensity projection in the deep learning neural network is that previously the deep learning techniques in the medical field just empirically bring some general techniques from the computer vision field, and a very few work view this problem from the domain expert perspective. And the maximum intensity projection is the way that the domain expert, or say the radiologist, view the MRI, view the brain vessel in the MRI volume. So that's why we're using the maximum intensity projection method.
Thanks. So Thanks for the answers. So it's time to move on to the next paper. So if any audience has questions, you feel free to post the questions in Discord and or exchange information with the author. So our next presentation will be given by Thu Oct and Xing. They are from Kent State University. So they will present the paper, Interactive Visual Study of Multiple Attributes, learning model of X-ray scattering images.
The title of our work is Interactive Visual Study of Multiple Attribute Learning Model of X-ray Scattering Images. We thank all co-authors and also thank the anonymous reviewers. X-ray scattering techniques help scientists discover physical structures of materials by analyzing the image patterns, and human experimenters must apply their domain knowledge to interpret the features in the image to select for the follow-up analysis. However, an X-ray equipment generates up to 1 million images per day, so the scale of the image data set often imposes a heavy burden. Recently, the deep learning models are employed in classifying and annotating for X-ray images, but the lack of proper explanations and the absence of control of the decisions would make the model less trustworthy. While considerable effort has been made to make deep learning interpretable and controllable, unfortunately, the existing visualization tools are not specifically designed for the classification models of X-ray scattering images, because it requires extra considerations in finding how the learning model performs for a diverse set of overlapped images attributes, and how the coexistence of attributes may affect the classification result. In response, we developed a visual analysis system for users to interactively study the model prediction with respect to the multiple structural attribute of X-ray scattering images. The X-ray scattering dataset has 70 attributes in total, covering 3 different aspects from scattering patterns, experimental conditions, and implied material structures. The 4 samples show the diversity of image attributes. The pre-trained model ResNet 50 was modified in the previous work by Wang for the classification of X-ray images, where the loss function was the sigmoid function. We extracted vectors for 3 representative spaces to analyze the performance of the model. The vectors in these spaces were also pre-processed with dimension reduction algorithm for the visualization analysis. We integrate representative embedding spaces of model to allow users to observe X-ray images and their relationship in these spaces. The error rate is a distance of a prediction vector and the true label vectors of the image. It is indicated by the transparency value. The darker, the larger error rate. The data are clickable to check the details at the bottom. The dot for the same image can be highlighted simultaneously to find how the model processed this image by the relationship of its neighbors in these spaces. Since the data point has their own natural similarities in high-dimensional spaces and also in the embedded spaces for their distributions, it's better to study them in groups. Here the gallery view gives a quick comparison for all images for 2 groups. They are sorted according to the number of contained attributes for each image, and they're also hoverable and clickable. The parallel coordinate chart for the metrics of model performance are also provided for each attribute in the selected group. The statistic of the same attribute in different groups also can be highlighted for a quick comparison. The attributes are sorted according to the number of related images. We can disable them and filter them with interesting attributes for analysis. The top coexisting attribute table lists the basic information for all different combinations of attributes, consisting of name, total number of images with actual labels, and the total number of images with the correct predictions on all these attributes. We can directly select any row for further analysis. We also have the hoverable and selectable matrix view for correlation, mutual information, and conditional entropy in both true space and prediction space, so the attribute relationship and the model performance on them can be found. The attribute set also show the model performance. The black and white circles indicate the model detected and not detected attributes. The images falling in each prediction scenario also can be selected as a group. These selected images in a group can be further clustered for drill-down study by K-mean and dbSCAN. In this panel, each point is visualized by an attribute flower with the encoding of model prediction. The subgroups of these images can be validated by the metric scores computed in real time.
In this case, we select a dense group with a high error rate in actual space to study in detail. In the performance measure view, since the attribute is sorted according to the number of related images, we found that linear beam stop contains an outstanding total number of images. In the clustering view of prediction space, the red petal on all flowers also indicate linear beam stop attribute dominate in this group. In this bottom cluster, all flowers are correctly predicted. We can click and check in the detail views. They look similar, except the image 62 has a blue background with a needle shape under the beam. However, the learning model gives correct prediction on this attribute. On the top cluster, most images are wrongly predicted. For example, image 38 and 44 fail to detect the linear beam stop attribute. They are detected as VIS beam stop or circular beam stop instead. Since the 6 raw input images at the bottom have the same actual label, and they are also visually look similar. It is interesting to check how they are separated in the feature space and also check the issues. We found that when the validation scores are optimal in the feature space, image 1 to 39 is in the same group with image 4, 38, and 44. Also, in the embedded feature space, image 1 to 39 is far away from image 62 and 54 in another group. That means there are some difficulties for convolutional neural layer to find the similar low-level image features, and therefore the fully connected classifier also confused and gave different prediction of beam stop types. This shows that the X-ray scattering attributes of different types of beam stop are quite hard to detect because of the small size and especially with a dark background. Therefore, this visualization system helps scientists to identify the weak point of a learning models. In this case, we will investigate the model behavior of 3 coexisting attributes to find the problem in these attributes. From the coexisting table, we have identified 3 attributes of interest: many rings, ring, and strong scattering. The attribute set shows different combinations of these 3 attributes according to the model prediction. We select 2 groups. One group contains 6 images where many rings are not detected, and the other contains 3 images where strong scattering is not detected. Then we drag and drop both groups to study in details. Both galleries of images show the high variation and diversity of X-ray scattering structures. But both groups share the same attribute, rings, and it can be correctly detected. The red group of the feature space are separated far away. It is interesting that image 77 is very close to the image in the green group. So we open these 3 images for further investigation. These images share the same feature of the rings attribute, and their center roughly lies on the corner of the edges. In image 77, the details shows the many rings has also been detected, but other images have not. This helps scientists to identify the model may not perform as expected, because the rings in image 296 is not complete as image 77. Since the features are extracted, the fully connected layer may need to be improved, such as using other classifiers like SVM. Next, we can find images in the green group are close to each other. They are sharing the same specular background. It also contains a large number of pixels with high intensity values. This may cause many ring attributes difficult to be detected. As a result, it indicates that many ring attributes need to be labeled and be separated from the other types. This can help scientists to perform further analysis in the future. We notice that the correlation matrix does not show the corresponding relationship for BCC with other attributes in the prediction space. However, this doesn't match with its truth facts. The similar thing also happened on FCC attribute. Therefore, we randomly sample out 500 images for study. Those images either have BCC or FCC attribute and also their true label vectors. T clusters are formed on the ACT panel, and this is an abnormal group compared with the other two dense groups. We can select them and check those X-ray images to find the possible reason. BCC and FCC are two unit cell structures. Typically, since the atom in a unit cell can only form one structure, the two structures are mutually exclusive to each other. However, the domain expert explained it as possible two structures can be superimposed to let them fall into these detected spatial cases. The other two large clusters fall into the normal cases, where each image has a single attribute of these two. But they are not well separated in feature space and prediction space. They just form a single large cluster with two color data points mixes. It means the pre-trained model has issues and it failed to distinguish the two attributes. We can look into the model performance in the group study panel. The precision recall and accuracy are all zeros for both attributes in two groups. It could be the reason that the model is not well trained due to the lack of the data with these two attributes. Since the features of these two attributes are too subtle, all other attributes may dominate or override the feature of these two attributes. So we can check the image for the details. It looks like the pattern is still on the rings, although they are hard to distinguish between BCC or FCC. So the model may have a lack of data images with these two attributes in the training process. Later, the model developer found the bugs. The label names are mismatched in the label pre-processing, so that no data are labeled with the true attribute for training. We present an interactive visualization system for understanding the learning model of X-ray scattering image with multiple attributes. The system allows users to visually discover the representative embedded model spaces. User interaction are supported to compare selected image instances and study their prediction result among the correlated attributes. In the future, we will add an effective labeling tool to improve the accuracy and effectiveness of the labeling process. Besides, it is good to extend the work for model debugging and refinement by taking neurons and different network layers into account.
Okay, thanks for the nice presentation. So we got a question from the audience. What does the color in the correlation matrix represent?
Yeah, okay. Thank you for your introduction first. And for this question, the color in the matrix are represented either for true data space and the other is for prediction data space. So we have the triangle to show both them together. So then for the same pair of the attributes, so user can compare what is the relationship of these two attributes in the true space and also compare the model prediction performance at the same time.
Okay, so I have a question. So can you quickly comment how did you work with scientists and how do they have a what are the feedbacks for your tool?
So we also showed one case there. We find a by using this tool, the domain scientists find they have the labeling issue one attribute called cubic, face cubic, face body cubic, and another is the center face cubic. Both are mislabeled. So then in the prediction, the performance are just a 0 for the accuracy. So that they find the issue like the mislabeling of this data, and then they can improve the labeling for that to attribute. That is one example. Yeah.
Okay, thanks. All right, so let's thank the authors again. So we will move on to the last presentation of this section. So the paper is a volumetric isosurface rendering with deep learning-based super resolution. So the presenter will be Sebastian Weiss from Technical University of Munich.
Hello everyone, my name is Sebastian Weiss and I will present our work Volumetric Isosurface Rendering with Deep Learning Based Super Resolution, published at TVCG 2019. The basic idea is to start with a low resolution rendering of an isosurface. A neural network takes this image and upscales it to a high resolution image with additional shading information. But why do we care? Why do we use a neural network when we can simply render the high resolution image? The answer is that rendering is not for free. The rendering time roughly scales linearly with the resolution of the datasets. While a low resolution rendering is cheap to compute, at a high resolution of, for example, 512 to the cube, it already becomes challenging to have real-time performance. Using a low resolution image in screen space reduces the rendering time. And a neural network for upscaling has a performance cost that is independent of the volume resolution. Therefore, for large datasets, we see a point where it becomes more efficient to use a super resolution network instead of rendering the full resolution. The downside is, of course, that the network results in an approximation and introduces errors. Therefore, we see applications mostly for interactive exploration and foveated rendering tasks, where slight errors are acceptable. The proposed network builds upon several related works. Here we summarize the most important of those. For single image super resolution, Wang et al. Are among the first to propose a network architecture that is capable of real-time super resolution. Sagar et al. Proposed EnhancedNet, a high-quality and fast network architecture. The network architecture is also used in our work. For video super resolution, the follow-up paper from Sagar et al. Introduces a way to improve the temporal consistency of the predictions. Nalbach et al. Proposed deep shading, where a neural network is learned to infer the final color and advanced rendering effects like ambient occlusion from deferred shading buffers. We build upon that idea that our network also estimates ambient occlusion. Next, we provide an overview of our processing pipeline. First, a low-resolution rendering of the isosurface is performed. Note that we use the mask, storing if the ray hit the surface or not, the surface normal, and the depth as input. Not the shaded color image, as using color instead of normal and depth decreases the quality of the reconstruction. The mask, normal and depth maps are then passed to the super resolution network. It produces high resolution images of those. A fixed differentiable screen space shading is then used to assemble the final color image. Additional to the mask, normal and depth, the network can also learn to estimate ambient occlusion, similar to deep shading by Nalbach et al. This greatly improves the visual quality without sacrificing any performance. If applied to animated sequences, the proposed method up to now leads to severe flickering artifacts, introduced by the lack of temporal consistency. This is because each frame is completely processed independently of the other frames. Sagar et al. Introduced a way to improve the temporal consistency, as shown here. The output of the previous frame is warped by the optical flow and then used as additional input to the network. the optical flow can be directly extracted during ray tracing. Together with a loss on the temporal consistency, this greatly decreases high-frequent flickering in the animations. The network was trained on images of a ejector, that's the dataset shown here as well. For a quantitative analysis of different loss functions and several image metrics on validation data, we refer to the paper. Here, as an example of the evaluation, we analyze if we can give bounds on the maximal error introduced by the network. If we look at those two images, on the left the super resolution and on the right the ground truth, they are almost visually indistinguishable. But if we take the difference of those images and scale them, errors become visible, especially among the silhouettes. To get empirical bounds on the error on the validation data, we can look at the cumulative accuracy. These plots are also called REC curves, and at the x-axis the allowed error is plotted. Along the y-axis is the percentage of pixels that fulfill this desired error bound. If we look at the color, for example, our proposed network in blue sadly only reaches 100% of pixels at an error of 1.0, meaning there will always be an error in the predictions. But if we compare to the baseline methods like bilinear or bicubic interpolation, the network always outperforms those. Meaning the baseline also always introduces errors and always have less pixels within a desired error bound. This already shows that the network at least can't be worse than regular interpolation on the validation data. For further quantitative evaluations, we refer to our paper. Next, we demonstrate that the super resolution network can generalize to novel datasets that were never seen during training. First, a CT scan of a human skull at resolution 256 to the cube is shown. From the low resolution input, the network can predict a high resolution version. The quality is comparable to the ground truth. Next, a CT scan of a human thorax is shown. This is an especially difficult dataset as the high frequent details or noise in the stomach region are very challenging for the network. One can see that the network fails to predict the high frequent details in a temporal stable way. Finally, a Richtmal-Meshkov dataset at a resolution of 1024 to the cube is used. It shows many fine details and larger concavities. The super resolution network can accurately reconstruct the high resolution image with ambient occlusion in this case. Here you see the ground truth for comparison. Next, we highlight two example applications. First, for interactive exploration, rendering the full resolution dataset is often too slow for an interactive experience. The two most common solutions are to reduce the volume resolution, which leads to massive loss of details, or to reduce the screen resolution, which results in flickering due to undersampling. Here, the proposed method helps by upscaling the image to the full resolution. And then after the camera movement stops, the image generated by the network can then be replaced by the ground truth rendering again. As a second example application, we demonstrate how the proposed method can be used in a forwarded rendering. Here, a full resolution rendering is only used in the focus region, shown under the mouse cursor. In the vicinity, only a low resolution rendering is used. If the focus region is moved around, one can see a transition from the low to the high resolution image. Now when the network is used in the vicinity instead, the differences are much less noticeable. This is advantageous as it is less distracting for a human observer. In the focus region, the full resolution rendering without any error is still used. To conclude, we presented a super resolution framework that takes low-resolution renderings of isosurfaces and upscales them to high-resolution images. The network also generalizes well to novel datasets without the need for retraining. And we've shown that it can outperform high-resolution rendering on large datasets, even though the network itself has quite some high constant cost. We see possible applications mostly in the field of interactive exploration tasks and forwarded renderings, where hard real-time frame rates are desired and small errors in accuracy can be neglected. For future work, we would like to extend the approach to direct volume renderings, and furthermore, the method currently only works with a fixed super resolution factor of 4 times. Instead, we would like to use a form of adaptive sampling, where more samples are taken in more important regions. For a first step into that direction, we refer to our follow-up paper on arXiv, Learning Adaptive Sampling and Reconstruction for Volume Visualization. In this work, a first network learns an importance map, which is then used to select the locations for the sparse samples. A second network then reconstructs the final image. This whole pipeline can be trained end to end. The source code is available at the link below. Thank you for your attention, and I'm happy to answer any questions.
Okay, thanks for the nice presentation. So we have a question from the audience. So can you comment a little bit about the data collection and the preparation process?
Thanks for the introduction, first of all. Related to the data collection, so we took the ejector data set. It's a data set with multiple time steps. We sampled several time steps, several resolutions, and several ISO values. And from those collections, from those data, we also selected various views. And yeah, this made out of our data set then. Yeah.
Okay. So I have a quick question. So how difficult is it to generalize to direct volume rendering instead of surface rendering?
It's pretty straightforward. So the most difficult change is that you have this dependency on the transfer function, and this brings in a lot of difficulties in the data preparation process. You need to generate training data where all these different color variations of the transfer functions are included. And you have to be aware of any color shifts and everything that the network might introduce.
Yeah, that sounds a promising direction. So I think we are running out of time, and I think it's a time to adjourn. So here I would like to thank all the authors for the great presentations and all the answers to the questions. And I would also like to thank all the technicians and the student volunteers to make this session possible. And also I would like to thank all the questions from the audience. Right, so hope everyone has a nice rest of the day. Right. Bye.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. Connect to the data you care about. Sort, highlight, drill down, or filter your data in seconds. Add calculations to extend your data. With Tableau, you can keep on asking questions in the data until you discover the root cause. Tableau. Answer questions at the speed of thought.
Visualizing the performance progression of machine learning techniques is often achieved by plotting the accuracy in a line chart. For specific tasks such as multi-class classification, they hide important factors such as inner-class confusion and instance-level details. We propose Instance Flow, a tool for interactive visualization of the evolution of classifier confusion on the instance level.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. With Tableau, you can keep on asking questions in the data until you discover the root cause. Share your analysis securely. Your entire organization can access these interactive dashboards from any browser or mobile device to find their own answers. Tableau. Answer questions at the speed of thought.
Hi everyone, I hope you're doing well. I'm Haikuan Park from Georgia Tech. I'm very excited to present Bluff, a visualization tool to interactively decipher adversarial attacks on deep neural networks. Deep learning is now commonly used in many domains. For example, in the medical field, deep learning models can estimate the treatment effects on patients. On the road, we can see self-driving cars using computer vision technologies. However, deep learning models are vulnerable to adversarial attacks. An adversarial attack applies carefully crafted perturbations on data inputs and fools a model into making incorrect predictions. Adversarial attacks jeopardize many deep learning-based technologies, especially in security and safety-critical applications, such as data-driven healthcare and self-driving cars. Due to the threats of the adversarial attacks, people cannot confidently use deep learning models. To overcome the vulnerability of deep learning models, we need to understand how the adversarial attacks permeate the model's internals. Also, for a better understanding about adversarial attacks, it would be worthwhile to examine if and how an attack strength changes how the model produces incorrect predictions. For example, it would be useful to know if a stronger attack exploits the same neurons as a weaker attack does, or if those sets are completely different. We present Bluff, an interactive visualization tool for discovering and interpreting how adversarial attacks mislead DNN into making incorrect predictions. Our main idea is to visualize activation pathways within a DNN traversed by the signals of input data. For given input data, an activation pathways consist of neurons that are highly activated and the most influential paths. Activation pathways represent what features are detected and how those features are related to contribute to the final prediction. To understand how the attacks manipulate the neurons and the paths inside the models, Bluff visualizes the activation pathways of both benign inputs and attacked inputs. That is, Bluff finds and visualizes the most activated pathways given benign and attacked input data. Bluff also visualizes the most inhibited paths by the attack to uncover where the attack is blocking the signals to the benign path. Also, Bluff visualizes the most excited paths by the attack to uncover where the attack stimulates to induce the activation pathways going towards wrong directions. The Bluff interface tightly integrates three coordinate views. It consists of control sidebar, graph summary view, and detail view. Here, a user inspects why a deep learning model misclassifies adversarial giant beta images crafted by the projected gradient descent attack as armadillo. In the main graph summary view, we visualize the activation pathways of benign and attacked input data. Here, each vertex represents a neuron. When hovering over a neuron, Bluff shows the detailed information of the neuron. The detailed view for a neuron shows a feature visualization and example data that visualize what feature the neuron is detecting. For example, for giant panda images, this neuron looks for face of animals that have white furs and dark eyes. Feature visualization is a synthesized image that maximizes the corresponding neuron's activation. Dataset examples are patches of images from the training data that highly activate the corresponding neurons. We also show how the neuron's median activation will change according to different attack strengths. Here in the graph summary view, The neurons are represented with different colors based on their roles. The green nodes are the most important neurons only for the original class, giant panda, which means they are highly activated by benign giant panda images. The blue nodes are important neurons only for the target class, armadillo. The orange nodes are the most important neurons for both original and target classes, giant panda and armadillo. The red nodes are the neurons that are highly activated by only successfully attacked images. These neurons are exploited by the attack to induce the incorrect prediction. By exploring the activation pathways, PGD successfully perturbed pixels to induce the brown bird features, an appearance more likely shared by an armadillo than a panda. Both armadillo and brown birds have small, roundish, and brown bodies. The brown bird neuron then contributes to the armadillo misclassification by activating more features such as scales, bumps, and mesh. By using the options in the contour sidebar, users can interactively filter the neurons and connections to visualize. For example, they can select to visualize R graph, or only highlighted neurons, or only pinned neurons. By using the highlight pathways options, users can select which activation pathways to visualize, such as most activated or most inhibited, excited, or most changed by the attack. By using the comparison mode, users can compare how attacks of different strengths have different activation pathways. In summary, we developed Bluff, an interactive system to understand how adversarial perturbations flow of the learning model. Bluff visualizes most activated, inhibited, excited activation pathways after the attacks, and provides flexible comparison of attack escalation. Thank you all for listening. I'm happy to take any questions.
We present a high-quality tube rendering method for 3D line datasets. GPU-based raycasting is used to render line segments as rounded cones, to allow for smooth connections along individual lines and variation in radius. We support transparency by a novel approach combining visibility order rendering with an order-independent transparency method. To improve depth and feature perception, ambient occlusion is employed.
Nowadays, data is often distributed and owned by different participants. There is an emerging need to provide a joint visualization, such as a TS&E projection, to serve as the full picture in data analysis. If the participants are privacy sensitive, how can we build a joint projection without data leakage? Conventional embedding algorithms, such as the TS&E, are designed for single-site computation and require data centralization. Privacy leakage may happen in 3 stages in the visualization pipeline.
Blockchain has gained more attention and its applications are emerging. We collect 76 blockchain visualization tools and systematically classify them into 5 aspects: target blockchain, blockchain data, target audience, task domain, and visualization type. In the end, we look at open challenge in blockchain visualization.